Hello, this is our Teams demo of our SCOMP Modulo Division Peripheral. Today we're demonstrating our SCOMP Modulo Peripheral, a hardware accelerator that performs division and modulo operations for any SCOMP program. We'll explain how it works, show its API, demonstrate edge case behavior, such as divide by zero, and then walk through two application examples using the DE10 board to illustrate how the programmer will use the peripheral. Our peripheral provides fast hardware division and modulo inside the SCOMP architecture. It accepts two unsigned inputs, a dividend and divisor, and it computes two outputs, the quotient and the remainder. Functionally, this unit replaces the need for software loops and subroutines that a typical SCOMP program would need to perform division or modulo. Instead of dozens of instructions, we reduce the entire operation to a single hardware request followed by a done flag. At a conceptual level, the peripheral works like this. Whenever the CPU writes new values to the dividend and divisor registers, and then writes a 1 to the control register, the peripheral internally triggers a division operation. The peripheral uses a clean 5-register memory mapped API. At address 90, we have the dividend register. Address 91 is the divisor register. Address 92 is the control register. Address 93 is the quotient register. And address 94 is the remainder register. This API is intentionally minimal. Every divide operation uses the same 5 registers in the same pattern. This guarantees predictability and makes the peripheral easy to integrate into any SCOMP project. Here is the complete usage pattern for the peripheral. First, the user will write the dividend to address 90 and then write the divisor to address 91. They can then begin the operation by writing the constant 1 to the control register 92. They can then pull the done bit in mod control until it becomes 1. They're then allowed to read the quotient from 93 and read the remainder from 94. This sequence never changes regardless of the application. It's consistent, simple, and extremely easier for the programmer to follow. Next, we'll demonstrate how the peripheral behaves when the divisor is 0. Division by 0 is undefined mathematically, and our peripheral must handle it safely. When the divisor is 0, the operation still transitions normally, and the done bit still gets set, but the quotient and remainder outputs are not guaranteed to be meaningful. Essentially, the done bit will be set immediately before any division or modulo operation is actually done. This will cause the quotient and remainder registers to keep their initial values. This is to help make sure that the user's software will not crash when running the program. The divide by 0 flag is given so that the users can manage these situations smoothly. We now show a short example video demonstrating this behavior in action.
So this is a test of our edge cases. Here you can see that we're putting 103 into the dividend and 0 into the divisor. In that case, the user will decide how they want to handle that case. In this situation, we wanted to load 255 and now put it to LEDs, which we can see here.
As stated in the video, we chose to turn on all the LED lights if divide by 0 was detected, but the user can manage this edge case however they'd like in their own SCOMP program. So to visually summarize everything so far, the CPU will write 2 inputs, starts the operation, waits for done, and reads 2 outputs. This simple producer-consumer model makes the peripheral both easy to use and easy to embed inside larger systems. Our first application is a modulo guessing game. Each round generates a dividend and a divisor. The peripheral computes the remainder, and the game uses this value as the correct answer. Because the peripheral completes modulo operations immediately, we can run many rounds per second without burdening the CPU. The game demonstrates the peripheral performing repeated division operations reliably and interactively.
So this is the test of our modulo game. First, we're going to flip all the switches down. And now we can see that our dividend is 15 and our divisor is 2. 15 mod 2 is 1, so all I have to do is flip this switch, and the game will flash 3 times to signify that our answer is correct.
Our second application is a real-time digital clock. We compute seconds plus 1 mod 60, minutes plus 1 mod 60, and hours plus 1 mod 24. Each wraparound is handled using the modulo peripheral. This turns what would normally be multi-instruction branch chains into a single hardware call. The timekeeping logic remains compact, readable, and reliable.
Logic basically runs through the entire assembly code for seconds, minutes, and hours, and we can see the looping timer here. I'll reset it to see how it actually goes.
To summarize, our modulo peripheral provides fast hardware-driven division and modulo. a clean and consistent API, a simple pattern that works for every type of application, compatibility with all SCOMP programs, and ease of integration into clocks, games, calculators, counters, and more. Our demonstrations show not only the correctness, but also the general usefulness of the peripheral. Thank you for watching.